Here we are at our 1.47 notes, just looking at some various theorems. Now, the first one says that all polynomials are continuous everywhere. And that actually makes sense because if we had, for example, y is equal to x cubed plus 2x squared, let's just say plus 5x plus 6, notice that this is just some polynomial. The reason why, though, this is continuous everywhere is that there's really nothing that this is being divided by, such then that you would end up with like an undefined statement or a removable discontinuity. So as a result, all polynomials are actually going to be continuous everywhere. Like if you were to kind of graph this thing, you would just kind of see an image. This is just a really, really rough sketch, but you guys can kind of see that it's just going on forever and ever, and it's not going to be, like, there's no vertical asymptotes or holes. Likewise, the sine and cosine functions, those will go on forever and ever. As we know, sine and cosines are just waves, so that they just oscillate back and forth like this, but they are continuous throughout the entire, from negative infinity to positive infinity. The tangent inverse, ooh, that's a bad one, but tangent inverse looks something like this. And so that does go on from negative infinity to positive infinity, and that would be continuous as well everywhere. Looking at e to the x, again, that's just a function that looks something like this, but it is in fact continuous everywhere. There are no vertical asymptotes or holes at all. Now looking at the nth roots, this is where things start to get a little tricky, but if you recall back to Algebra 2, anytime that you have an odd nth degree, you would see something like this guy. In fact, it's really kind of similar to that tangent function. So anytime you have that nth odd root, you would see something like this, where it is in fact continuous everywhere. Where you are having an even root, if you recall back from Algebra 2 as well, you would see functions that do something like this. All right, so the smallest thing that x could possibly be here, it can't quite be 0. Or I'm sorry, it could be 0, but then you just end up with the y value 0. But again, that would work if you had the nth even root. So as long as your x values are larger than 0, you're good. Now we also have the natural log function. So the natural log function looks something like this. And again, it's kind of following that same idea where as long as x is larger than 0, you're good. All right? Because again, you can't quite be 0 from the natural log of x. So that's why I'd be going down toward negative infinity. And then lastly, we have the sine inverse and cosine inverse. Those are also continuous anytime, though, that x is in between -1 and 1. To kind of help illustrate that, I've gone ahead and graphed them. Here is the sine. You can see that it is, in fact, from -1 to +1, and that it is also continuous throughout the entire interval. Likewise, here is going to be the cosine coming up. And you can kind of see the same thing between -1 and +1. So this theorem actually really helps us in determining some kind of like future calculations, because as long as you know that certain parts of polynomials or certain pieces of functions are in fact continuous, then if you start combining all these different types of functions together to create one massive function, then you can say that the entire massive function, if they're all individually continuous, you can say then that the massive function is continuous as well. And that's really what transitions us into some theorems dealing with some operations with continuous functions. Now suppose that f and g are continuous at a specific value a. Then the following have to be true. The first one, we have f plus g. So in other words, if you have some function, you add another function, g, if they are both in fact continuous individually, f plus g is then going to be continuous specifically at that a value. This likewise works for subtraction. If you subtract the two functions together, it will also be continuous at, again, that specific a value. If you are multiplying these two functions together, as long as both of them are individually continuous at the specific a value, then if you take the product of that, it will also be continuous at that value. And then likewise, division. There we go. And this has to work, or this last one works just as long as that bottom function is not 0 when we plug in that a value. So this might seem a little bit confusing for right now, but we're going to see various examples of how this is actually holding true. But just a really quick one. If you were just taking, like, example, this first guy, f plus g, if we had some polynomial, we'll say he's x squared, and then we have this other function, we'll just say that he is 6. Well, x squared is continuous throughout the entire time. So, for example, this would be the graph of that function. Likewise, g is also going to be continuous, being that you just have that number 6. So, for example, it's just a constant at 6. Well, then if you just combine the two, since they are both in fact continuous altogether, then x squared plus 6 will also be continuous itself. All right, so that's pretty much how these definitions are actually working. Is really you're kind of having like polynomials that are kind of brought together by different, basically, sub-functions. All right, but again, as long as each one of them are continuous, then the entire group collectively should be continuous. So again, though, that is the theorem from our 1.4 set of notes.